Alright, let's continue. Let me open the table of content first. Hopefully my internet connection is fine. Well, let's see how it goes. Okay, we are still in chapter 28. Look here, still on homework simulation section. Let me open that. Okay, we are still in this homework simulation. The last question that we take a look, if I remember correctly, is question 7. Now let's take a look at question 8. Okay. Thread log 66, this one. And now let's take a look at Peterson. Okay. Now let's look at the code peterson.s, the assembly file which implements Peterson's algorithm mentioned in a sidebar in the text. Okay, study the code and see if you can make sense of it. Okay, so array of 2 integer, its size 4 byte, load address of flag into fx register. Okay. Load address of flag into fx register, access flag array with, guess this is the, what is it called? The address, maybe. Oh, so this is the base address. This is the index of the array, right? And this is the, what is it called? The size in this array, in this case 4 byte, because we have integer, I guess, where index is the register holding 0 or 1. Okay, index array contains 0. Okay, flag. Okay, this is what is it called? Indexing, something like that. To integer, okay. Turn count. Okay, we copy, I guess, the, what is it called? The base address in flag variable here, or global variable, I guess, into fx, right? This one, load address of flag into fx. So we got the base address of the flag array in the fx register. Assume that id is in px, 0 or 1. Scale by 4 to get proper flag address. Oh, right. Yeah, maybe the official term for this is scale, but I usually think of this as the size in the, what is it called? Array type, maybe something like that. But we can also think of this as scale. Scale by 4 to get proper flag address. So basically the array is every 4 byte, something like that. the element or item in the array, I mean. Okay, self now copies to cx. Okay. Assume that that id is in px. Okay. And now we copy the thread id into cx, I assume, and then we get that, and then, well, add that, I guess, because we have negation in the self, it become one negative self, or maybe I feel like doing this, what is it called? Might be, what is it? Make easier to understand, maybe something like that. So basically the value of this is plus by this value, and it turns out that the value of cx is the negation of self here, or the thread id, I guess. It is kind of interesting, the negation of thread id. Okay, acquire. I'm not sure if we need 0 in here, but well, I feel like we can, what is it called? We only need to write this. I mean, if I understand correctly, right? This will become something like this: fx plus 0 plus px multiplied by 4. So I think 0 in here might not mean anything, maybe, unless I misunderstood something. Okay. Flag, alright. Yeah, we are indexing, right? And then put 1 in the index of the array, and then check term. Okay, spin, alright. Oh, interesting. One negative self. AX. Oh, because, okay, so the index here, instead of px, we are using cx. It is something like this, right? Okay, so this is the difference between this line and this line. Okay, there's that. Or if not equal 1, finish. Okay. Yeah, if what is it called? If the maybe element in the index one negative self not equal 1, skip pass, loop to finish. So we immediately finish. If the element or item in this index not equal 1, okay, just label for fun, not need that. Okay. Alright, compare turn and one negative self. Okay, If it is equal, going back to spin here, checking again. I guess. Oh, wait a minute. If turn equal one negative self, go back and start spin again. Go back and start spin again. Okay. That make me wonder. Oh, maybe because of the interrupt that the turn here might have different thread ID. Maybe so that when the turn equal one negative self equal, what is it called? The current thread turn, or yeah, I'm still not sure about this one. One negative self. Is one negative self the current thread? Maybe. So if turn equal the current thread, we are spinning again. Is that it? If the thread ID equal the current thread ID, one negative self, or yeah, what is one negative self? Or maybe one negative self is the next turn. Is that it? Yeah, before that, what is one negative self? I need to understand this first. I assume self is the current thread. Wait. Maybe self is the current thread ID. So maybe okay, assume that ID is in PX, right? So we are passing, I assume the current thread ID into CX, and then negate that, and then add that to 1, something like this. But then what is this? One negative self. If self is the current thread ID, maybe maybe it is the next thread ID. Yeah, I'm still not sure about that. mean if the turn equal one negative self. Oh. Okay. If self is the current thread ID, maybe one negative self is the ticket number, I guess. For the current thread ID. So if the ticket number here is the same, right? We are spinning again, going back to this one. Maybe, but then to finish. Skip pass loop to finish. To finish, I mean. Disable. Okay. In case, make sure it's outer's turn. Oh, wait, what? Outer's turn. Skip pass loop to finish. Okay. Release. Make sure it's outer's turn. So does that mean one negative self in here is the outer's turn? So this one in this section or instruction, I guess, does that mean the turn in here is the current thread turn or the next thread turn? Yeah, I'm kind of confused. Okay, Okay, If flag not equal 1, skip pass. EX. So if, okay, maybe something like this. The ticket number for the next thread ID, maybe if the okay, yeah, let's try understanding this. If the next turn, maybe something like that. next turn, if the next turn flag is not 1, we go into, or the current thread go into critical section according to this, I guess. So we check if the element or item in the flag here, in the next turn flag, maybe something like that, is equal to 1, 2, maybe, or not equal to 1, I mean, not equal to 1, which means the current thread is the only one holding the flag, and then we can going into the critical section. But if the next turn is also 1, move turn AX. I'm still not sure about this one. Compare turn and 1 negative save. We save turn in here, right? So we compare that with 1 negative save. I mean, maybe there is some interrupt, so that there's a chance that 1 negative save is different from turn, maybe something like that. So 1, check if the ticket number, I guess, ticket number is if turn equal 1 negative save, it's the same as the next thread turn, I guess. We are still in the same thread. I assume something like that. Go back and start spin again. In the same thread, current thread, what is it called? And if the ticket number is the same, the next turn is we are still for the next thread ID next turn, and if the ticket number is the same as the ticket number in current thread, maybe maybe something like that. We are spinning again, but then what if it is not equal, you know? Let's set the flag item is equal 1, right? And the turn also not equal with the turn in the current thread. So basically it is different ticket number in another thread. Are we just going to the critical section? If the next turn, okay, maybe doing it like this, maybe. If the ticket number is different, the ticket number in current thread, we are entering the critical section. And then release. Okay, yeah, this one is confusing for me. What is going on in here? Compare turn with one negative self. Go back and start spin again. And then if the flag is not 1 or is equal 1, I guess, the flag on the next turn equal 1. Oh. Yeah, if the flag on the next turn equal 1, we are entering critical section, or we are checking if the current turn equal with this 1 and negative self. Okay, let me check. What is it? Peterson. Okay, I think this one. Just load and store are used. The idea is to ensure that two threads never enter a critical section at the same time. Load and store, assuming they are atomic with respect to each other. true on early hardware. Okay. Oh. Wait a minute. If flag only 0 and 1, right? That ID of color. Okay, make it other thread's turn. Okay, this is the next thread turn. Okay. Spin with, well, it's not your turn. So does that mean the other thread turn? Not necessarily the next thread turn. Is that it? For some reason, developing looks that work without special hardware support become outraged for a while, giving theory types a lot of problems to work on. Of course, this kind of work become quite useless when people realize it is much easier to assume a little hardware support. And indeed, that support had been around from the earliest day of multiprocessing. Further algorithms like the one above don't work on modern hardware due to relaxed memory consistency model, thus making them even less useful than they were before. Yet more research relegate to the dustbin of history. Okay, so make it other thread's turn. So if the other thread's flag is 1, and what is it called? And other thread turn equal, what is this? 1 negative self. Other threads turn equal our own turn? Maybe. So other thread still holding the flag, but we still get our turn. Make it other thread's turn. So yeah, I assume this will change when we have interrupt. Maybe. Self. So if the other thread turn equal our turn, maybe we are spin waiting. I mean, if the flag equal 1, right? But the turn here is false. We are not spin waiting, right? So how do this turn false? When turn not equal or when turn equal our turn. But then it's still holding the flag. Yeah, I'm still confused here. What is going on in here? Maybe we can solve that by checking out the code or running the code. I mean, what kind of different values, what kind of different behavior do you see? Make sure to set the thread ID appropriately. Okay, right. Let's try this out. Wait a minute. Thread logs. Okay. Thread logs. Not touch and set. But Peterson. Okay. What is it? PX, right? The thread ID here 0 or 1. Okay, 0 and 1, and then should I also track, is there any memory? Okay, yeah, maybe we can track turn and count. Maybe turn and count, and then also track or trace register 2. Like for example BX and CX. I mean, I don't think FX cannot change. Okay, BX and CX. Do we also need to track AX? Maybe. So AX, BX, CX, and the condition code. Okay, something like this. Okay, let me check. Okay, naked CX. Okay, I assume naked 0 mean we still got 0 for this instruction. At 1, okay. Copy that. Okay. That make me wonder. Can we also track this memory? I'm not sure. Or maybe something like this. I don't think we can, but let's try this out. Yeah, we cannot do that. Okay. Alright. Okay, move to 1. Okay, CX is 1, and then turn. Move that to turn. Okay, to AX. Wait a minute. move Cx to turn. Okay. I assume this is, what is it called? On the outer thread flag, be something like that. It is 0. Okay. Is it equal 1 or not equal 1? I guess yes. So we enter the critical section here. Move. Okay, move 0 to. I assume this one is, what is it called? Turn off the flag, maybe. Yeah, release the flag. Okay. Extern. That is still 1. Okay. Oh, wait a minute. How many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Maybe let's add the header count to 15. Yeah, put the, what is it called? The header FA 15 instruction or something like that. Oh, Cx become negative 1. Yeah, because Cx, or maybe the thread ID is 1, right? Okay, and then become 0. Okay, maybe I should. Okay, move this first so that I can see this one. Okay, move 1. Okay, X move the turn and then check, I guess, if another turn holding the flag, and it looks like it is not holding the flag, so we enter critical section. So is the assumption here only to thread? I guess. Let me try again. Okay. Why do we need, oh, yeah, we need to get that so that we get the outer thread. Maybe assume that the thread is only that one and that 0 and 1. Okay, add 1. another thread ID. Okay, this one, and then move one to the flag. Oh, wait a minute. Okay. Move one to the current thread flag. Yeah, for this one, I mean px is the current thread ID, right? How do I explain this? Put one into current thread ID flag. Flag equal 1, something like that. And then this turn. If we move the CX to turn. Okay. So the CX in CX register, right? Okay. So CX hold another thread ID, not the current one, and then we check if another thread ID if another thread ID holding the flag 2, right? Okay, but in this case, yeah, let me explain this case first. Check if another ID holding the flag or not. If not, going to critical section. It's what we do here, and then release the flag for current thread. Turn, okay. And then make sure if the next turn maybe the next turn is another thread turn, this one, and then switch, alt and switch, and then doing the same thing again. CX holding another thread ID, right? turn on the flag, and then I think this one mean, yeah, I'm not sure if we need this one. Maybe in this case, oh, okay, so maybe we put the next thread or another thread turn in this one, and then check. Check if another thread holding the flag. If it is not holding the flag, enter enter the critical section and then hard. Now I'm kind of curious. With different value of interrupt frequency, right? Interrupt frequency. Yeah, I'm kind of curious. Maybe put this one, or yeah, or maybe put this one. Right. What scenario when turn not equal one negative self? Maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's try using interrupt frequency 10 and see. Okay. Move count. Wait a minute. 1, 2, 3, 4, 5, 6. Oh, right. Okay. Yeah, we check for the flag in this case, and it is not holding the flag, so we kind of continue. We are entering the critical section here, hard, right, and then we're just doing the rest of thread 1 instruction. So maybe interrupt in here. Maybe. Or in here. Okay, 1, 2, 3, 4, 5, 6. Let's try that. Okay. Turn right. Turn is 0. Okay. Okay, turn is global variable, right? There is that. I mean CX is restore, not 0 anymore. Okay. Maybe let's do this. Oh, okay, move turn. This one, right? We move like to this. Oh, okay. In this case, we also move like to this one. And it turns out that ax not equal 1. Ax equal 1, I mean. Oh. Equal 1. So does that mean the thread 1 holding the lock? If that one holding the lock, then we check the turn Cx equal ax. In this case, no. Cx not equal ax. So yeah, I'm kind of confused. If I understand correctly, right? Cx is, what is it called? Another thread turn, right? When we are on thread 1, here Cx becomes 0, and when we are on thread 0, Cx become 1. So I assume what is it? Let's say flag 0 and then flag 1. So I assume in this case we check whether the flag was set. Okay, where is it? Ax. Thread 0. Okay, maybe something like this. And then thread 1. Okay. Or maybe this instead. Check if flag 1 is 1 or not. From where is it? From this one, I assume. Taking the value of flag on thread 1, and if it is one, we continue check the turn. So if the turn equals Cx, which I assume if the turn here equal the current turn, maybe something like that. We are spinning again, but if the turn is not equal, oh wait, if the next turn or the other thread turn equal, oh, let me check previously before the interrupt. I assume turn in here is the next thread turn. Maybe. So if Cx is not equal turn, we are going into the critical section. Yeah, I'm still not quite sure how to interpret this. Turn is 1, turn becomes 0, right? And well, we if I understand correctly, okay, you know what? Maybe I can track the fx2. Okay, 100. Can I do something like this? No. Okay. P100. Yeah, I'm kind of curious about 100 and 101. The state of flag. Okay. Can if flag 0 in 100 address and address 100, flag 1 most likely in the address. Oh, not okay. Every 4 byte, right? So maybe 104. Okay, something like that. See, we set we set the value to 1 or the flag to 1, right? And at the same time we also set the value on thread 1 to 1 2. So boot flag either in what is it called? In thread 0 or thread 1 is 1, you know, if I understand correctly. Right, that's why this is false, because the other thread or another thread is equal 1, and I'm still not sure about this condition. How do we decide if both threads having the same flag, having turned on the flag, you know? It's like, what is it, no mutual. I assume the situation is something like this. On thread 1 we set the flag, and on thread 2 we also set the flag. No mutual exclusion. So how do we decide which thread going into the critical section? Yeah, this one. I am not sure. In this case we just, what is it called? We just have to interrupt right before jumping or continue into the critical section. How do we determine that? Spin 1. Oh, interesting. So in this condition, jump condition, okay, it looks like we are going back to this on thread 1. Let me try understanding this. Turn, okay, it is 0 and cx, okay, cx are x, cx is 0. Okay, so maybe test check whether check if the next turn is ongoing, maybe if the thread another thread is ongoing, but yeah, I am still not sure what CX in here hold. Is it the next thread or another thread or something else? And what this turn hold? What is turn? What is turn supposed to hold? And what is CX supposed to hold? Maybe that's how we decide the mutual exclusion, even though both, what is it called? Both flag is turned on. But yeah, I'm still confused. Like, what is going on there? Make sure it's other's turn. Oh. Maybe turns hold or can hold either the current turn, current thread, or another thread turn, and CX maybe CX hold the next thread turn. So maybe the only one that hold the next thread is actually the CX. Maybe. And because of context switch, the turn might change to the next thread or the current thread. And in this case, if turn equal the next turn, if turn equal CX, the next turn, spinning again. Maybe we are spinning again, or we are waiting for that turn to finish. Maybe. Okay, well, I guess let's continue this on the next session. It's kind of confusing, I guess. Like, both of this flag is turned on. How do we decide which one entering the critical section first? And I'm also curious how can people think of this algorithm? It is quite interesting. Okay, yeah, let's continue exploring this. Peterson, I guess. Where is it? This Peterson instruction with different value of interrupt, and maybe we will also try using the, what is it called? Using the scheduling to, yeah, with the exact thread run, right? For example, we already see the, what is it called? The behavior where the flag turned on, right? Now what happened? If before we release, oh, okay. And what happened if we keep going in thread 1 rather than having interrupt? I'm assuming the thread 1 is gonna keep spinning, maybe, and then we are going to the critical section on thread 0 finally. Yeah, let's leave that on the next session. Can you control the scheduling with the TSP flag to prove that the code works? What are the different cases you should so hold? Think about network exclusion and deadlock avoidance. I'm assuming this question 10 still talking about Peterson instruction here. Maybe. So we will explore this on the next session too. Okay, so I guess that's it for now. Thank you for watching and see you next time. Bye bye.